So welcome back, everybody. And it feels always better when we can be in a lecture hall than just teaching digitally. So yesterday we could not be here because the room was occupied by this kind of a post-education day for high school teachers. And to me, it felt a little bit strange because it was just like going back to COVID times when you're just sitting there and reading and writing and you don't see anyone. And finally, you see some people at least, right? It was a kind of deja vu feeling where you actually felt you're coming back to COVID times. Okay, so the topic we are dealing with now, I wanted to use the beginning of this lecture to remind you of some of the things which we looked at yesterday. And we are going to repeat a little bit about this classification and regression tree algorithm, which is normally called the CART algorithm. And this is actually pretty simple to implement. And yesterday's lecture was meant more to give you some of the basic elements on how you can set up a classification tree and how you can set up a regression tree. These are extremely popular methods. They actually don't involve much mathematics, as you've probably seen. And it's very much more based on how you actually subdivide and split the trees. And there you can use different recipes, as we saw yesterday. You can use something like the entropy, or you can simply use this Gini factor, which runs through the different features and finds out which of these features is the most pure one. That means that when you're deciding on what is your root node in a tree, you try to find out for the classification case which feature which you have among the set of features, which one is the one which has less mixing from the other features. And that means that you would classify that as the most important feature. And the example which we looked at yesterday was an example which we just cooked up, where we looked at the trend in grade, in average grade, whether you were above or below the average grade. And then you correlated that with the output from a new course, and you looked at whether you got a grade above or average for a next course, depending also on the number of hours you studied and the number of hours you slept. And based on the calculation of this Gini factor, we could then decide that one of these features, the grade trend, the hours slept or the hours studied, was the most important one, defined by the Gini factor, which then allows you to decide which one is the purest one. So if you have only one feature, which is then the one you're left with, that means that your Gini factor or the entropy is actually equal to 0, because then all the information is just encoded into one quantity. And the probability for that quantity is then equal to 1, right? And when that is equal to 1, then your log, if you're looking at the entropy, is equal to 0. Log of 1 is 0. And that's one way to classify it. And then clearly you also have to take away the unlikely cases with 0 probability. And that's why you define log 0 times 0 equal to 0. So the entropy is a much used quantity because it gives you a function which is continuous. The entropy is also, or the log function is additive. It's also easy to calculate the derivatives of these functions. And at the same time, however, compared to the Gini factor, is actually a quantity which requires a little bit more floating point operations. But in these kind of decision tree algorithms, what you typically do then is actually to switch either between the Gini index or this entropy. There are other algorithms, but the dominating one is actually this CART algorithm. But let me quickly remind you a little bit about the setup of these kind of trees here. There's a reason for why I do this. So the tree itself has some nice pedagogical features because you can easily display the features in the system and tell which is the most important one. And it's understandable. You can actually present it to people who have no background in, let's say, mathematics or machine learning, you can read off from the tree the essential messages. However, it becomes limited, as we discussed yesterday, because it can easily lead to overfitting. You can really fit things so precisely by making your tree deeper and deeper or taller and taller that we have basically no predictive power on data which were not included in the training. This is normally compensated by making ensembles of trees. And one of the methods we are going to look at today is called bagging, which is actually trees. You construct a forest of trees by bootstrapping. And in that case, you're going to construct a forest of look-alike trees. So these become more like a homogeneous forest. It's quite fun because many of the concepts, I mean, like you can trim the tree, which is normally called pruning of the tree. You can make, it's actually called pruning algorithm. So you can make a tree very deep, but that becomes time consuming. And then you can start pruning away some features. You can make homogeneous forests, so you can use random forests, which is widely used as a method for classification and regression. And it does actually pretty well. And random forests is more heterogeneous forest. And the methods are so simple that it's actually not so difficult to write your own code. When you have, for instance, like the codes we discussed yesterday for the Gini factor. Then these decision trees, they can be treated as a weak learner in what's normally called boosting methods. So boosting methods means that you start with a weak learner and you keep boosting it by it in an iterative way. And that leads to one of the methods which is widely used, which is called gradient boosting. And there is a very popular library which is called extreme gradient boosting, or XGBoost, which has performed extremely well on many of these competitions, machine learning competitions. And XGBoost is not a method, it's actually a gradient boosting, but it's a highly efficient parallelized library, which does extremely well on especially classification problems. So these are the methods which we are going to look at today. First, we're going to look at ensemble methods, but I wanted to remind you just quickly about what we did yesterday. So let's just bring this up here before we move on to the slides again. So let me just bring this. So what we did yesterday was actually to look at this type of trees. So we had a classification problem, classification and regression trees. And this is normally called the CART algorithm. I mean, you shouldn't be biased by me because I'm mentioning this algorithm all the time, because there are other ways of also splitting the trees. So, but this is by far the one which is most used in basically all applications. And if you now look at the classification problem, like the one we had yesterday, so let's just write it down here, just take a kind of overarching look at it. So you would find then a root node, and that would typically be dominated by the smallest entropy, or smallest Gini factor among the features which we have, all features. So as I said, as we said yesterday, the Gini factor, if that is exactly equal to 0, it means that this root node contains only one feature. And typically when you have only one feature, there is nothing to be done, right? Because then the tree terminates. But normally in the beginning, you would, when you're looping over all the features which you have, so like in the case with the grade, the final grade, which was the output, we looked at the grade trend, the hours you slept and the hours you studied, So these three things are the features. And each of these features had a class or attribute which could be above average or below average. And then we took each feature and then we calculated the one which had less mixing from the other ones, or the one which had the smallest Gini factor. And then, by the one which has the smallest factor, we would then decide which is a root node. And then, when we've decided a root node, we find the binary splitting. So we would have a true and false. And then we would have a given set of data, which result in the true case and in the false case. So in the true case, then, we would look at, again, the features, the subset of features, and then we would recalculate the Gini factor and find the one which has the smallest one again. So we could now find a new Gini factor for a new attribute. So this would be a new feature with the smallest Gini factor. And this could again be split into true and false. In the example which we looked at yesterday, what we had was that when we had the true case and we found that the average grade which people had, the trend of all grades, was a dominating feature. And then we saw that the hours studied was the next dominant feature. And this ended up in the leaves. So this is normally called an internal node. And in this case, we had, if I don't remember wrongly, we had the 4 cases where people got a grade which was above average, and 2 cases with a grade below average. And then when we split this, we ended up with just the final leaves. So in this one, you would have something which was above average, and in the other one, it was below average. And these are then the final leaves. And then we could continue here. In the case which we looked at yesterday, we actually ended in a case where everybody got a grade below average when it was false. And then that terminated there. But it doesn't need to terminate. And then you would simply just continue with the true false. So this is a new feature again. And this could perhaps end in the final leaves here. So this true-false splitting are normally called the branches. There is another algorithm which we haven't discussed, which is also used in the literature, which is called the ID3, that allows you actually to be able to split in more, make more splits at every node. But the most common one is actually the binary splitting, because that tends to contain more data when you move down. When you split it up in more branches at every tree, you can easily end up in a situation where you fragment your data. So the favored recipe is actually to perform a binary split at every tree level, at every node, and then you continue till you have pure classes. So in all these cases here, you will find an entropy which is 0 or a Gini factor which is 0 in all these cases, and they would just contain a certain element of observations. So the basic recipe here is you take all the features you have. So if you're dealing with a cancer data, that cancer data, which we have been discussing up and down, has something like 30 features. And then you would loop through these features and calculate the Gini index by simply calculating the frequency of each entry which you have. The way to look at that, so let me just quickly remind you of one of the examples which we looked at yesterday. So let's go back a little bit and look at one of the examples here in the Jupyter notebook. So I'm not going to repeat everything which we did yesterday, but I wanted to remind you of one of the kind of made-up data sets which we had. And then we're going to go back to, so this was the first data set where we looked at the grade trend, hours slept and hours studied. and you will find the calculation of all these Gini indices in the handwritten notes from yesterday. But there is another data set. If we take a look at this one, this is a data set now which has 4 features, and then the output is whether you're going to ride your bike or not. So I'm obsessed with the road biking, so that's why you will find a ride here. But you could actually change that with a run or something else, or just a hike, which perhaps is a little bit more pleasant. And then you have 4 features here: outlook, temperature, humidity. And each feature here has an attribute or a class. So in this specific case, we have 3 attributes for a feature outlook, and these are sunny, overcast, and rain. So what you would do then, when you're finding which one is your root tree for this specific case, you would then calculate the Gini factor for the outlook or the entropy for the outlook. You would calculate the temperature, the same Gini factor for temperature, for humidity and wind. And then when you have that, you would then decide which has the smallest Gini factor, and that would define the root node. And then when you find the root node, you have reduced the number of data because you have peeled away one of the features. And then you would continue then, so suppose now that the outlook is actually the most important one. Actually, this is going to be the one when you do the calculation which has the lowest Gini factor. And that's, in a way, it's understandable. And then when you've done the outlook, which is the main root node, you would then have temperature, humidity, and wind. And then you would continue and calculate the Gini factor for that. And you would find the biggest one and then split the tree again and again and again till you actually have the final leaves, which are just pure and have a Gini factor equal to 0. So it's a way to, in a very, how to say, very simple way to actually generate the branches of the tree. So if you just look at this table, just to quickly remind you of the way you calculate the Gini factor. So let's just take the outlook. And if you have that in front of you on the laptops, because I'm going to go back to my whiteboard here and just calculate the one for the outlook. And if you look at the outlook here, you see now that you have 14 cases, and you have 5 events, sunny, 5 rainy, and 4 when the day is overcast. So that means that the probability for rainy or sunny is 5 divided by 14. So then you can calculate that probability, and that probability is then weighted with the probabilities for every single class which you have. So let's just repeat this calculation here. So in this specific case, we are going to look at the outlook Gini, and we are going to correlate that one, obviously, whether we ride or not. So let me just repeat that as another example, and then I'm going to give you the answer for the other ones, because when you've seen this yesterday and you're going to see it today again, it's not that exciting. So there's not a deeper insight into it, but I just wanted to repeat the exercise, which you can do then. So if we take the outlook case, so we would simply first start with the probability of the outlook equals sunny. And that we have 14 observations, and we have 5 for sun. And then we do the same with the outlook for rainy. And then that is equal to the previous one. And then we have the final one when the weather is overcast. And in that case, we have 4 divided by 14. Then we have to look at the different classes which we have for one specific feature. So we would then have to look at if outlook is sunny and we go for a ride. If let's just shorten this one. If sunny and ride. If we do the counting, and most likely you don't have it, we have then 5 cases with sunny, and we ride in 5 of the cases. And then we have the same if sunny and no ride. I just write no here. That is equal to 2 divided by 5. So the right case in case of sunny gives us a Gini factor, which is equal to 1 minus, and then I have 3 divided by 5 squared minus 2 divided by 5 squared. And that should be equal to 12 divided by 25 here. Then I can take the next one. If it's rain, if it's overcast, if overcast and ride. In that case, I actually have 4 out of 4. And if overcast and no ride, just write this as a no, this is equal to 0. And in that case, the Gini factor is actually given by 0. So G is then equal to 1 minus 0, which is equal to 0. And the final one is the rainy case. If rain and ride, then the probability is equal to 3 divided by 5. And if rain and no ride, P is equal to 2 divided by 5. Actually, I hate rain. I don't ride when it's raining. Sorry. Anyway, so in this case, we get the Gini index again when we do the math here, which is equal to 12 divided by 25. And when I do the Gini, the total one for the outlook feature, so this is the feature here, then I get 5, which is the total probability, divided by 14, times 12 divided by 25, plus 5. So this is weighted by the individual attributes which we have for the feature, the feature of the weather forecast or the forecast for the day. 12 divided by 25 plus 4 divided by 14 multiplied with 0, and that's going to give us 0.343. If I take the other ones, so this is the weather forecast. If I take the one on humidity, if I just repeat the calculations from that table, I'm not going to pester you with all these small details. And then we get the wind feature that has a Gini factor of 0.5. And then we have the final one, which is temperature, and that has a Gini factor of 0.405. So it means that the feature which is going to define the root node is actually this feature here. So that would be the root node, and then you have true false. And when you have this true false, you propagate on. So for the true case, you would then compute the Gini factor for all the other features which are not given by the weather forecast or the kind of prediction of whether we are going to have a sunny day, rainy, or a overcast day. So this seems to be the most important feature in this specific case here. But this data set are just made up. So just to illustrate how you can calculate these quantities, yeah?
How are we doing true false when we have 3 categories for the outlook?
Say it again. How?
In the other example, we have only 2 classes, either are above or below average.
Yeah.
Here the outlook can be 3 different things.
Yeah.
If you can't do a true false and then like split evenly.
So in that example, if you look at what we did yesterday, what happened then, if we go back to this one, what you had is that for the false case, it just terminated here. So there was no reason. And in this case here, you had 4 cases above and 2 cases below the average grade for the course. And then since you had looked at the trend, The only features which are looked at then was the hours studied and the hours slept. And in that specific case, the hours studied is the case which had the smallest Gini factor and which defines the second node.
But I'm wondering what condition are we setting for the root node? Is it we have to choose one of them? Is it sunny? Because we can't say it's sunny or rain because there's a third option.
Yeah. Now, so in this case, you have to, if we go back to the, so this could be a little bit random how you set up things there. So if we go back to the table here, so we have the outlook. So that's the main feature. So, and we have decided that that's the main feature. And that feature has 3 different classes. And then we try to calculate the Gini factor based on these 3 different classes. And then we do the same for temperature, humidity, and wind. And then you pick the one which has the largest Gini factor here. And in this case, with this data, you find that the outlook is the one which has the smallest Gini factor. So the Gini factor measures a kind of purity. So if you have a Gini factor equal to 0, that means that it's a pure system. But there will always be mixing in the beginning. So when you end up in the final leaves, so the final leaf have a Gini factor which has 0. They contain only one type of observations. Did that help? A little bit? Yeah. Okay, so we are coming back a little bit just to revisit the algorithms, but I just wanted to say something about the way a regression tree is going to look like. So if we go back to the whiteboard here. Yeah? You have a question, yeah?
Yeah, on the whiteboard, the
Yeah.
the sheet's high.
Yeah.
Given that there's only 2 classes, so if there's 2 classes, how can the Gini factor be bigger than 1/2?
If you have 2 classes, yeah, that's a good point. I may have calculated wrongly. I'm going to recheck the numbers.
The width is also the same.
Yeah, so that's a good point actually. So most likely, I actually did some errors in the calculations there. I'm going to recheck the numbers because I actually did it this morning early. So I'm going to check it, but I can give an exercise. Why don't you just take a look at it? So probably I may have mixed up something here. That's a good point actually. I think my number is a 0.3 actually, but I'm going to recheck it. Yeah. Yeah, I'm going to check it again actually. Okay, a good point. So sometimes it's better to have a program which automatizes this. Yeah. And in the slides, you'll find a program which does it. So let's look at the regression tree. And yesterday we discussed the basic algorithm. And typically the basic algorithm is you starting by splitting the data domain which you have in 2 slots, 2 equal slots. And then you try to optimize the mean squared error from the left-hand region and the right-hand region. So a typical domain here, suppose now you have only 2 variables, x1 and x2. So let's just remind ourselves of that. And let's suppose now we made a splitting here in different regions. So we have a T1, we have a T2 here, and we have a T3 and a T4. And here we have a region R1 and R2, a region R3 and R4 and R5 here. So your tree could look like this. So there could be a root node where you now simply have split according to T1. So as I said, the prediction you make for the variables in the different regions are given by the average of all the values in that specific region. So that's a prediction you make. So if you have 100 data points in one of these regions, your prediction is the average of these 100 data points. But that means that you can narrow down these regions, so it just includes only one of the data points. And then your prediction is the data point. But clearly, this leads quickly to overfitting. So one of the problems with decision trees is that you can make a perfect fit to the data, really perfect fit. So if your goal is to perfectly fit a data set, then decision trees is absolutely the best way of doing it. But then you have no predictive power, right? So this is a trade-off. But suppose now that you split it in two and you follow x1, then if this is true, so we put a t here, and false, then you could get a new one here, where you could say now that if x2 is less than t2, and t2 is there, so if it's true, you end up in the final region, which is R1, and you can see that. If it's false, you end up in the region which is called R2 here. Then you can continue here with the next branch, and then you could have x1 less or equal to t3, and if it's true, it terminates in R3. So I'm just going to bring this up here so you see it better. So if x1 is less than t3, you end up in the region R3. Alternatively, you need an additional splitting, and then you have an x2 less than t4. And if that is true, your prediction gives you R4, and if it's false, you end up in R5. So each of these slots, which you see here, R1, R2, R3, and so on, they may contain many observations. So for a regression type of problem, your prediction then is the average value of the observations in R1, R2, R3, R4, and R5. And you see that you can make this smaller, these regions smaller and smaller, so you can really nail down a given parameter. And as we discussed yesterday, if you go back to the slides, the way we typically do this, so let me just bring up the Jupyter notebook here. If we go back to where we were yesterday, the way you do the regression case is simply by splitting in different regions. So you can start with a splitting in two regions. And so you would have a given number of observations to the left of this point S, this splitting point. And normally this splitting variable can be chosen either as a midpoint, or you could simply choose that randomly. That's also fully possible to do, but normally in most algorithms you would split this at the midpoint, and then you have the to the left, not to the right. And simply then what you do is try to optimize the mean squared error for each domain here. And then you keep splitting and splitting and splitting till, and this is defined by variables like the depth of the tree. So remember now that we start with a root node on top, so this is a top-down approach. So our trees are just growing downwards instead of growing upwards. But you could think of you making the tree deeper and deeper. And the standard algorithm which is normally used is this cart algorithm we discussed yesterday. And so let me just quickly remind you of that before we move on to some other applications. So for the classification case, what you would do now is to, when you look at these domains, you would then take the number of entries in the left domain and the number of entries in the right domain, and then calculate the Gini factors. If you do regression, you would simply have the number of observations in the left slot divided by the total number of observations, calculate the mean square error, and similarly do the same thing for the right box. And then the mean squared error for each node here is simply just the calculation of which involves the average for that specific data set, which is given by this quantity here, just the average. and then minus the observations which you want to reproduce. So you can make these trees, you can make these splittings deeper and deeper and deeper. So the algorithm is very easy to implement, and if you feel tempted to do that, feel free to do so actually. Actually, we had for the final project, we had people who wanted to implement the decision tree algorithm and move on with that one to do bagging, boosting, and so on. But let's take a look at some examples here. So some of the examples are those which we discussed yesterday. And there's an example on how to compute the Gini factor and so on. Here's an example of where we now take a data set where we have x by some random variables, and then we have y, which is 4 times x minus 0.5, and then we add some random noise to it. It's a pretty simple data set. And in this specific case, when you look at the dependency on the depth of the decision trees, so in this case, we have a max depth equal to 2 and a max depth equal to 3. What you will see then is the types of depths which you have. And this, what you see here, this red line, this is the prediction you are making. And so this is a regression case. So the prediction here, the red line, is actually the average of all the data points inside that slot. And the same here, and the same here, and the same here. And then you can see that when you make the depth a little bit larger, you're narrowing down the number of data points you have in a given slot. And then your prediction becomes better and better, hopefully. And then you can actually, there's a variable which is called the mean samples leaf. And I invite you actually to take a look at, I never remember all these variables. I always have to look up. So if you go to the decision tree classifier or the decision tree regressor, you can find a series of parameters you can tune. So the set of hyperparameters can quickly grow here when you decide on how to run the tree calculation. But if we go back, you can now rerun this with a much more advanced tree. So you can have no restrictions, so that means actually you try to reproduce as much points as possible, or you can have a so-called mean samples leaf, and again now you see the straight lines here, they are the predictions which you make in this case. So it's pretty easy to actually set up your algorithms and try to reproduce what these libraries do for you. Now, as I said, the reason why I spent some time on it is that the decision tree itself is the basic algorithm, and that's used in making ensembles of trees, but it's also used in boosting methods, where the tree enters as a kind of weak learner, and it's quick to calculate, and then you use that one to build improved or improvements on your function. So let's just look at some pros and cons here. So it's easy to interpret. It's definitely not a black box. It's actually what we call a white box. So it's pretty transparent. There is not much advanced mathematics. And actually some people believe that they mirror human decision making, and compared to many of the other methods, they are very easy to explain. So as I said once, these are the things you can take your favorite tree with you to a party and then entertain people. As I said, I think I said it before, I have a nagging suspicion that that's the reason why nobody invites me anymore. Okay, but it's fun actually. I like decision trees. It's not very complicated. And you don't need to normalize your data. They actually can work on heterogeneous data. They can both handle continuous and categorical data, classification and regressions. You can find nonlinear relationships. However, you will see that there is something where they will fail clearly on. So if you go back to this whiteboard, let's do that. And if you look at the way we typically make the tree, if you look at this domain x1 and x2, where would it fail? So what I'm doing now, I'm just trying to reduce the data. And I said in one of the statements there that they are excellent for reproducing nonlinear relationships. What about a linear relationship? So if your function, suppose now the function you want to reproduce is something like this. It fails dramatically. It fails on the simplest cases, right? So a decision tree is actually, the way it's built up is you're just making these smaller and smaller boxes which contain your data. But if you have a straight line which goes through the domain here, you will have problems in being able to split up the region. So, but if you have the more complex data, it actually does a pretty good job. Okay, so let's go back to the advantages. So you can model interactions between different descriptive features actually. They can be displayed graphically. And you saw yesterday that a tool like a library like scikit-learn has a lot of functionality which allows you to describe easily the tree. You can easily make a nice plot of the tree. So like this cancer data, which has been studied zillions of times, it's very easy to make a tree out of it. So the problem, however, is that they do not generally have the same level of predictive accuracy as some of the other regression and classification approaches. And if you have continuous features are used, the tree may become quite large and hence less interpretable. It's actually when you have the large data sets like those which we are dealing with in project number 2, you will often find that neural networks do a much, much better job than a decision tree. However, since it's easy to overfit, there are actually types of improvements which are based on ensemble methods, and we are going to look at boosting and bagging. I love these names actually, all this kind of, I wonder who cooks up all these funny names. You have other problems. Small changes in the data may lead to a completely different tree, and that's also something to think of. There are also features with many levels may be preferred over features with less levels, since for them it is more easy to split the data set. So there are many such small details which make perhaps the decision trees a little bit less favorable. But then you can ameliorate that by looking at the methods where you are simply bringing together many trees. And one of the simplest one of these is called bagging. So that is just bootstrapping a set of trees. So what you're doing then by you bootstrapping your data, you fit a new tree to every bootstrapped data. And then every bootstrap is a new tree. The problem, however, when you bootstrap your data is that the dominant feature may always be there. So that means that your root node will normally, when you bootstrap the trees, the root node will always look the same. And many of the branches will look the same. So that means you're going to build a homogeneous forest. And when you do random forests, on the other hand, you can compensate for that, and you can get a heterogeneous forest where the trees are different. These methods have also their pros and cons. So if you look at these ensemble methods, so bagging is these bootstrapped trees. It follows also with random forests. They are better with overfitting, and as you will see, actually many of these examples, there is not a deep mathematical explanation. So many of these properties here, they follow from practicing with these different trees. So, and you will see that the bagging is something which can reduce the variance. Some of these methods can overfit. Gradient boosting normally reduces both bias and variance. Bagging and random forest tend to reduce variance, but not the bias. And you can deal also with sequential classification. So these methods here, so bagging and random forests, they take the tree as a tree which you can make as deep as you want. On the other hand, boosting takes as input a shallow tree, and you use that as a weak learner. And then in an iterative way, you can improve on the function which is going to describe your data. And all these methods here can be used both for classification and regression. So after the break, we are going to take a look at these methods, and like the bagging method, this is you doing a bootstrap. Instead of a polynomial where you call linear regression or neural network, you do a bootstrap on a decision tree. It's very simple to actually make your own bagging code. The random forest is also extremely simple to make. So these are codes which, if you feel tempted to explore these in project number 3, this is one possible path for project number 3, for instance. And we had people who did that last year and also the years before. I'm going to stop the recording, and then after the break, we are going to discuss a little bit more in detail these different methods. Do that. So what we are going to do now is simply to look at these ensemble methods, and the basic ingredient is a decision tree. So if you have been able to understand properly what we discussed, or you have a kind of feeling that you could write a code for decision tree, then you know that this is the entry point, whether you have a classification tree or a regression tree. So these ensemble methods are nothing but just an ensemble of trees done in different ways. But there's also another type of methods which are very popular, and you will find that in scikit-learn. So this is also something which applies to boosting. So I mentioned that the boosting methods, which we will discuss if we get to them at the end of the day today, but we will dedicate time to them next week. So the boosting methods, they can be grouped in a kind of way. So you start with a weak learner, and then can a group of people somehow arrive at a highly reasoned decision despite the weak judgment of the individual members. The aim is then to create a good classifier or regressor where you can combine several weak classifiers. So this is the basis behind voting, but it's also the basis for the boosting methods, where you start with a simple decision tree, a shallow one, where you can run the calculations quickly. And then the hope is that bringing together these repeatedly is that this hopefully can then reach a better judgment than the single individual tree. So normally the decision trees, you could replace decision trees with a cheap ordinary least squares. When you do a regression case, you could take a polynomial to first order and keep improving upon that. So when we're going to look at boosting methods, you're not limited to decision trees, but decision trees are used because they are quick and easy to implement as a weak learner. So the philosophy here is, can we use a cheap method computationally to make an improvement on the final result and get perhaps a mean squared error which is as good as possible. So one way to illustrate that is actually to look at tossing the coins. So let me just guide you through that. So a so-called voting ensemble. So if you suppose now you toss the coin only 10 times, then you know that the likelihood of getting a 50-50 may not be that high as if you were to toss a coin 10,000 times, right? So if you have some spare time problems, you could actually just sit down and toss your coin every evening and just count the number of heads and tails. I guess you guys have a lot of problems with spare time. So we have to make the projects a little bit bigger. Just joking. Okay, jokes apart. So you know that if you toss it 10 times, you could have 6 heads and 4 tails. But if you do this many times with 2,000, approximately, if you look at the probabilities, you should have a 10,020 and 980. And if you keep tossing them 10,000 times, then if you have this kind of coins where you are cheating a little bit, so there's a higher percentage for heads and 49 for tails. When you then do this 10,000 times, you're ending up in a likelihood of 96. It's not so difficult to calculate this likelihood of a majority of heads. So when you do it a few times, it may not be clear that you have a majority of heads, but if you do this many, many times, you will have this majority of 51%. And the example which you see here is actually just a simple example where we do this repeatedly. So we simply toss it with 10,000 times, and we have a probability of 51%. That is what is encoded here. And then depending on where you start, you may get different ways. So this is just a run many times. But you see all these runs now are just narrowing down. So this is the 51. You can see this line here. This is actually an example which I took from the textbook by Geron. And you see now that when you repeat this experiment many, many, many times, you're getting close to the probability of 51%. So when you run it a few times, you may be off, but when you keep running this, you will start seeing a pattern which emerges, and you're getting closer and closer to the ideal result. So this is an example of a kind of ensemble of experiments which you run, and where the idea is then to be able to make a correct prediction, even if you have a weak model in the beginning. Now, scikit-learn has a method which is actually called the voting ensemble, the voting classifier. And in this case, what you could do now is to use different methods. So you could use a random forest classifier. You can use a logistic regression. We have not described random forest yet. You could use a support vector machine classifier. And what it does then, it combines these three methods and then tries to improve the prediction by bringing together three different methods. And that's called a voting classifier. So this is one way of doing it, but it's not that much used. But you can see now if you do logistic regression, you have a 0.864, and then you can do a voting classifier. This is with, I think this was with, no, why did I printed 2 times actually. Probably I printed it 2 times because I'm so slow actually. I need to repeat everything. So this is just a print statement which just repeated, but that's the, I didn't see that before now actually. But this is the results which are interesting. So these three methods by themselves, they make a prediction which is actually less than the one you have for the voting classifier. What I wanted to show you now is actually the usage of bagging and how you can make an ensemble of methods in a very quick way by using Bootstrap. So bagging is widely popular. It takes a decision tree as a basic method. And in this case is that, as we have seen, these decision trees, you can easily overfit. And you remember from project 1 that when you overfit, you will get a high variance, right? So one way to reduce that is to bring many trees together. And so if we split the training data into 2 parts at random and fit a decision tree to both halves, the result that we get could be quite different. In contrast, a procedure with low variance will yield similar results if applied repeatedly to distinct data sets. We know that linear regression tends to have a low variance if the ratio of the number of entry points to the number of features we have is moderately large. So bootstrap aggregation is just what's called bagging. So we are making a forest by bootstrapping. And bagging typically results in improved accuracy of a prediction using a single tree. However, since you have many trees now, it can be difficult to interpret the results. So if you have a simple decision tree, you split it up, you can easily tell these are the main features, the most important things. When you do bagging and random forest, you lose this kind of simple way to interpret what is going on. And the typical way you would do that is to perform a set of B bootstraps. And there is an example in the slides here on how you can now make your own bootstrap. And what we are doing now is simply to let them construct a model where we change the level of the decision tree. So you remember in connection with project 1, the model was given by the complexity of the polynomial. So the complexity now is defined by the depth of the tree. So if you think of a regression problem, that means the more subdivisions we make, the deeper the tree, and the better we will classify. So the example you will see here is an example where we have a max depth of 30. I can make it smaller or not. So when I have 100 data points and I do 100 bootstraps, so we could just change this one now just to 10. And this function is a function, you may ask why I'm just coming up with the same function all the time. This is just a laziness factor. I'm copy and paste. So I'm just using the same function, and I'm making a fit of this function by simply bootstrapping. So you see again, in this case, the polynomial degree is no longer the polynomial degree, but it's actually the max depth of the tree. But I kept this poly degree to remind you of what we did way back in the beginning of the semester. We split the data and train test. I scale the data. I think in this case, there's no need to scale the data, but it's also something which is done by default here. And then I set up a simple tree, which is a tree of depth 3. So you can compare that. So that's just one decision tree. And it's a pretty shallow tree. Then I set up my prediction for the shallow tree, the simple one. And here I now run over increasing depth. And as you can see here, this is my bootstrapping. So this is where I do the resampling. Then I train a new tree every time. So in this particular case, I'm going to build a forest of 100 trees because I do 100 bootstraps. And I'm just reshuffling my data. And then I'm also going to plot the bias and the variance. And what you will see then is something like this. So it's not a polynomial degree, it's the max depth of the tree. So if you look at the mean, this is the mean squared error with a tree of depth 3. And you see the mean squared error is pretty large, it's 0.5. But then, when I now make an ensemble of 100 trees, you would see something like this. So you can see the mean squared error actually goes down together with the bias, as we know. And then when I reach a tree of level 7, 8, this seems to stabilize. So what I see here is actually that the variance stays small. So decision trees with bagging can actually stabilize the variance and keep it small. So let's just increase the complexity here and just play around a little bit. So we could make a tree of depth 30 and just rerun here. So it's pretty fast. And in this case, you see something like this. So you still see a pretty small variance, and the variance compared to what you saw in project number 1, or in the examples we had with ordinary least squares, when we increase the polynomial complexity, the variance tended to increase when we pass this overfitting region. So decision trees with bagging, that means bootstrapping, have this property where you can actually reduce the variance in general. And the methods are pretty simple to implement. So decision trees are normally pretty popular. The only problem here now is that the trees end up being lookalikes. And this is something you can fix by choosing the data sets a little bit more randomly than we do here. So what happens is that when you do this bootstrapping with a data set, with a full data set, you would then easily end up in a situation where your root node is the same for all the trees. And this leads us to the topic of random forests. And so if you look at that one, they provide an improvement of bagged trees by way of a small tweak that decorrelates them. So when the trees are all lookalikes, what you will have is larger correlations between the trees. So how can you then grow trees which are not lookalikes and which then have less correlations among each other? And this is what the random forest tries to do. So what random forests is, as you did in bagging, we would build a number of decision trees on bootstrapped training samples. But when you build these decision trees, each time a split in a tree is considered, then you pick a random sample of your features or predictors. So suppose like in the cancer data, where you have 30 features. So instead of picking all 30 features, because when you pick all of them, you would produce the same nodes. Now you pick randomly, say only 5 of them. And then you construct the Gini index with these 5, and then you continue splitting your tree. So that's a random forest. So instead of picking all the features, you pick a subset of the features, and in that way you can build different trees all the time. So when you do the root node, by not picking all the features, so like in the grading case, we found that the trend was a dominant feature. Next time we could leave out the grade trend and just pick our studies and our hours slept, and then just construct a tree based on these two. So that will produce a different tree. And you would have less correlations between the trees. So, and this is something which is also done in a very ad hoc way. So the typical number of features or predictors you would pick would be something which is often proportional with the square root of the number of features you have. So if you have 100 features, you would then pick something like 10 features. Yeah? Say it again.
You keep this the same as you go down a tree, or
No.
decrease M?
You would then decrease M when you go down a tree. That's the standard recipe for random forest. So that means that the tree would not become that shallow actually. So if you have few features, it would stop quickly. So the random forest algorithm is actually runs something like this. So you would then grow something like, say, B trees. You would draw a bootstrap sample from the training data in your X matrix. And then you grow then a random tree based on the bootstrap data by repeating the steps which I outline here. So you would then select, so this actually should be an insert in there. We select M less than P variables at random from the P predictors features. And then you predict the best split point among these features using, for example, the count algorithm. And then you split the node into daughter nodes, and then you keep going like that. And then you output the final tree and make predictions by the regression type or classification type of problem. So the example which you see here is actually an example for the decision tree, where we now have introduced the cancer data again. So we have a decision tree classifier. There are no restrictions, so we try to grow as a deep tree as possible. And here we also compare with logistic regression. We do a support vector machine. We have a standard decision tree, but then we also have the random forest here, where we actually include something like 500 trees. And then the splitting criterion is, in this case, the entropy. You can choose entropy or Gini, typically. And then we make our prediction and calculate the accuracy using cross-validation. And this is something we would compare all the other methods with. And you can see now the data set here. So we have a data set which is split into 426 for training, and we have 30 features. These are the test data. And you can see that all these methods are actually doing pretty well, except for the plain decision tree. So the plain decision tree normally does not as well compared with these other methods. You can obviously make the decision tree deeper and deeper and deeper. And if you then include random forests, you see now that you're actually getting a accuracy score, which is actually pretty good. It's actually better than the one you got with the logistic regression and support vector machines, which we will discuss in just a little bit more than a week. And if you look at your confusion matrix here, you have the true false 98% and the true negative as 97%. And then positive, negative, no, false negative and false positive are pretty small here. So the prediction with a random forest is actually better in this case than what we had with standard logistic regression. So this is actually pretty good. Any questions so far? So you see the basic philosophies here is something which is also easy to implement if you want to write your own code for it. So the splitting you do is based on a smaller fraction of the number of features which you have. And then basically everything is just, again, reusing the standard decision tree algorithm for the splitting, whether you're doing a regression or classification calculation. And then you can plot these different curves, the cumulative gains or the ROC curve and so on. Just to remind you, because these are things which are useful to plot, also in connection with project number 1, where you're, if you want to look at the cancer data, the cumulative gain and the ROC curve is something which is useful. So recall that the cumulative gain curve shows the percentage of the overall number of cases in a given category gained by targeting a percentage of the total number of cases. And this ROC curve, so that's the gains curve, that displays the diagnostic ability of a binary classifier as a discrimination threshold is valid. And it plots the true positive rate against the false positive rate. So these are just ways of displaying the data. I tend normally to just plot the confusion matrix. I think that's often pretty straightforward and it's easy to understand. So, but these are kind of measures which are pretty common to use when you are looking at the score of your data. So you see now that we're doing actually better. So the question is, can we actually improve this? Now, for this Wisconsin data, we're going to see what, when we use extreme or gradient boosting, we're actually going to get a score of 100%, which is pretty good. So you can compare the trees with the random forests and bagging if you want. So they're just examples. So the thing which we are going to start a little bit with now is actually these boosting methods. So this is we're actually wanted to pick up now, and this is something we will continue with next week. And boosting methods are actually extremely popular. So let me try to explain to you the philosophy behind these boosting methods. So the basic idea here is actually to use a weak classifier as an input, and in order to create a good classifier. So if you think back of this voting problem, where you could have weak classifiers, you were bringing together many of them in order to produce a better result. So with a weak classifier or a weak regressor, what you normally think of then is something which produces results which are just slightly better than you tossing a coin. Just slightly better. And often these are cheap and fast to evaluate. So what you would do then is that you iterate a weak classifier in order to modify the function which you're looking at. And in each iteration, what is done then is actually to give more emphasis to the data which you predict wrongly. So you give a weight to the data which are wrongly predicted. So that means that in the next run, the weights which are the data which are wrongly predicted have a slightly higher weight. So you can, in the next iteration, you can focus on fitting those which you failed to reproduce in the previous iteration. And then you move on till you have obtained a very good fit. But your entry point is just this weak classifier or weak regressor. So what I'm going to do now is actually to switch back to the whiteboard, just to slow down the pace so that we don't stare at the screen all the time here, or just stare at the slides, which is better. So this is a topic which we will also spend some time on next week when we deal with boosting and gradient boosting. So this is a very popular set of techniques. And as I said, the basic philosophy is to use a simple approximation and then iterate based upon that by putting emphasis on the data points you failed to describe. So the basic, let me just state this again here, the basic philosophy that is to use a simple function, and this could be classification or regression, or we could say a simple approximation, or approximation here. And then iterate in order to improve the reproduction of the data. And what you're going to notice is actually that this kind of approach is not so different from what you're doing with neural networks. So I'm going to try to give you a kind of link there, because the basic approach now mimics a lot of what you are doing in project number 2 here. So in order to improve the reproduction of the data. And with the data, obviously that means the data set we want to fit. So let's now look at the regression case, because the regression case is a little bit simpler. And maybe it's simpler to also understand. So let's just focus on that one. So what we are going to do now is just to use the standard mean squared error. And we have a function which is given by the data set which we have minus this y of I tilde. And for simplicity, I'm just going to call this y of I tilde as a function f of x of I here. So this is just the standard definition of the mean squared error, and that defines our cost function, which I now just write as a c. And then we want to optimize this function. Now, what we're going to make now is an approximation to this f. So the next thing, so we define this f of x of I as a function which is given by some parameters. And let's see how we can define that. Which is, we define this as, so we are going to approximate this f of x, and now I just skip this f of x of I, as a function which depends on a parameter m here, x. And this is just an iterative, a function which is determined iteratively. And it has a parameter beta of n. And this is multiplied with a function which depends on x and some parameter gamma. So this should be n here. And parameter gamma of m. So this beta of m is just a parameter which we tune at every iterative stage. And this b is a function which now could be our weak regressor function. It could be a polynomial of first order, which is simple to evaluate. And this is often the thing, we want to have something which is easy to evaluate. So let me just give you an example of that. So what we are going to do now is also that our function, the function we want to optimize, is actually this 1 over n, and then we would have an I equal 0 up to n minus 1, and then we have y of I minus this function f of m of x of I. And this function now depends on these different variables. So typically what we would have is something like this. So if, when we put m equal to 1, then our function f1 of x could be given by some function f0 of x. which we could put to 0. So we could just initialize by putting that to 0, plus some function which we call beta 1, which is a constant, multiplied with b of x of gamma 1. So that's our first iteration here. Then, at every iteration, we just optimize the mean squared error. So by optimizing the mean squared error in every iteration, we get new parameters, beta of I and gamma. And then when we have optimized that, we produce a new intermediate step, fm of x. And this fm of x is then given by the previous values, x0, plus a beta of m, of b, of x, and of gamma of m. Now, this is just one possible way of defining this function. There's nothing which hinders you of having other types of function dependence and parameter dependencies. So if you now look at a typical example, we could now have a very simple case, example here. We could put this f0 of x equal to 0. And then we could simply say that our beta of x of gamma 1, this is the first function here, is simply given by 1 plus a parameter gamma times x. This is normally what we would call a weak regressive function, because it's just a straight line here. Then, what we would do next is then to optimize. And when we optimize them, we need to calculate the derivatives of the cost function. So we are looking after every iteration, n, till we reach the final one. So we have defined a function here which depends on a set of such iterations. So in every iteration, we optimize the cost function. And we find the parameters gamma and the parameters beta, which minimize, in our case, the mean squared error. So that means that we optimize, and now we calculate the derivatives with respect to these parameters. So this will be an argmin of these parameters gamma and the parameters beta. And then we would calculate the argmin of the function which we have is 1 over n, not m, but n. And then we have a sum over all the data set. And in our case, we have y of I minus f of m minus 1 of x of I. And then we have minus, and then we have the parameter beta. And then we have this function, which is an easy function to evaluate. And then we have the x of I, and then we have the gamma of m, or just gamma here, because now we just take away the index, because these are the quantities we want to evaluate. So in our specific model, if we look at the example we have with a first order polynomial, that would give us the following. We would have a sum of 1 over n, and this is the one we want to calculate the derivative of y of I minus fm minus 1 of x of I. And then we have minus beta of 1 plus x of I multiplied with gamma squared. And then we take the derivatives of these two quantities, and then we can use whatever we want, a gradient descent or whatever, to drive these derivatives to 0. So the derivatives in this case are pretty simple, because what we get then, we take the derivatives, since we want to optimize the derivative of the cost function with respect to the parameter beta. We want them to be 0, and this is the same as minus 2 divided by n, and then we have a sum over I, and then we get 1 plus gamma of x of I, and this is multiplied with y of I minus beta times 1 plus gamma of x of I. And this quantity here is then something we want to put to 0. And similarly, we can then calculate the derivative with respect to gamma. I'm not going to set up the expression here, but then when you have these derivatives, and you would typically find the roots of these quantities, if you don't have analytical solutions for them, you would find the roots by gradient descent. Then you have the optimal parameters. And then when you have that, so with the beta, what you have then, since this is the first iteration, with the first iteration here, what you would get then is an f of 1 of x, which is given by f0 of x, which we put to 0, plus a beta 1, plus, of 1 plus a gamma 1 times x. And then you plug that one in again, and you optimize again. And then you keep calculating derivatives again and again and again, till you've done this n times. So this is the basics of a boosting method for the regression case. Now, what I haven't done here is actually to try to emphasize the points which I failed to reproduce properly. So this is something which we can add in addition to what we see here. But what you see is the basic philosophy of boosting methods. And when we come to regression, then we are going to multiply this kind of cost function with a function which penalizes, or which is given by the weights, where you penalize more those variables which you could not reproduce properly. Now, before we look in more detail here, let's now take a look at something which we have done before. So this kind of procedure, so this would just continue. So what you would have then is that an f of m of x would then be equal to f of m minus 1 of x, the previous value, plus the parameters you find, beta of m, plus a gamma of m, multiplied with x. And then you would continue till m is equal to m, which would be a number of iterations which you have fixed. So this is actually something, so this kind of additive expansion mimics what we have seen with neural networks. So it's normally called an additive expansion. It is at the heart of many learning techniques. And you can see that if you now think of neural networks. So let's see how that comes through, right? So if you think of neural networks, and you take now a single hidden layer, what you have then is that your function, b, which we had defined above here, so this function is something which we can decide upon. So in this specific case here, we have defined this function b to actually be given by a first order polynomial. But the function b here could now be, if we now think of the input and the output, so we have just one single hidden layer, this could be given by our activation function. This is the output from the hidden layer, and that will be given by some y0 plus some gamma 1 times x, just to give you an example, where the gamma 1s are the weights, okay? And then when you run a neural network, so your sigma here of t, that could be given by the sigmoid function. And gamma is just a set of parameters. In our case, that would be the weights. So x is multiplied by the weights. And if you now think of a neural network, is actually, in a neural network, you're doing this many, many times. So it means that you are improving upon this function or this output. So your B here, which you have here, is something you would change every time you have done a back propagation stage. And then you perform a new forward step, and then you produce a new output. And then you repeat this many times, the number of iterations you do, in order to get the best possible mean squared error or the best possible accuracy score. So this kind of process, which you see in the boosting method, is actually something which we do in many of the machine learning methods. And a neural network is just another example. So in our case, instead of having this specific function dependence, so we made an assumption here, up in top here, with the boosting methods, is that we have some kind of behavior like this. In a neural network, this function is now given by your activation functions, where you have the input times the weights, and that produces a new value for y. And then you keep doing that till your value for y, when that enters the cost function, it produces the best possible cost function you're after. So next week, we are going to look at different ways of doing that. And one of them is called adaptive boosting, which is simply called ADA boost. Not ADA grab, but ADA boost. And then when we've done that, we're going to look at a method which is slightly better, which is called gradient boosting. But the basic philosophy, if you've gotten the basic philosophy here, that's the basic philosophy for these methods, where you iteratively try to improve the quality of the function by using a simple function. In a neural network, we keep the sigmoid or the activation function. We don't change that. So that's our basic entity. And in this case, we could have a weak learner, which would be the basic entity. And then we just keep improving upon that. So next week, we are going to look at how we can implement this. Actually, the ADA boost method is extremely easy to implement. And we are going to show how you can do that for the regression case and for the classification case. And then when we've done that, we're going to look at the gradient boosting, and then we're going to look at examples on the classification we get and regression we get with these different methods and compare them with other methods. Okay, so that should be the plan for next week. And when we're done with that, we are going to move into support vector machines. And if we get time, we will take a look at some unsupervised learning methods. And then it's unfortunately the end of the semester. It's always sad. Okay, guys, enjoy your weekend and feel free to ask questions as always.